Welcome to the first workshop of the eFORT project. This is the first in a series of 4 workshops, and today we will focus on the Italian pilot site. My name is Carla Clu. I am from RINA, and I am involved in the project's dissemination and communication activities. And now I'm pleased to leave the floor to Jesus Torres from CIRCE, who will be moderating today's session. And please remember to send your questions through the Q&A box at any time during the workshop. So thank you very much. It's a pleasure to have you all here today. And Jesus, the floor is yours.
Thank you, Carla. Good morning. Hello, welcome everyone. I am also pleased to host this practical workshop of the eFORT project, and thank you all for joining us today. I will be moderating the whole session, as Carla said, and we will see the agenda right away, as I think that, well, it was shared along with the invitation, so it should be known by everyone. But just a quick reminder of what we have for today. I will be in charge also the first welcome and introduction that for more or less 15 minutes will take us through the general aspects or a general overview of the eFORT projects before moving on to the Italian demo site, which is what brings us here today. After an initial introduction to the whole demo site, we will have 3 different panels focused on specific technological aspects that have been or are being showcased in our demo site. I will introduce the speakers when their time comes with every panel, and we will get to know them right away. After that, we have prepared a Q&A session. First, we expect to pose some questions for every of the speakers from our side. We count on an initial debate where I will ask some questions to deep dive into the technologies and innovations that will be presented. And hopefully we will have some time to introduce some questions from the audience. And finally, a quick wrap up where we will have the chance to reflect on the main insights and what comes next for the project and for the demo site. What I was showing was the agenda you all have with the invitation, but prior to every panel or presentation we have, just for you to know, we will recap the agenda like this to show where we are. So, with no further ado, let me devote some minutes to introduce the eFORT project which is hosting this Italian demo site focus on distribution network automation and intelligent operation. As for general figures of the project, as you can see, we are heading into our final stretch. We have more or less our final 6 months in front of us, because the project took us 4 years from September 2022. Quite a relevant project. As you can see, we have a quite representative coverage of the European Union in terms of countries, diversity of climate situations, which are important for the grid, and different realities of the grids. We are pleased to have in our demo sites the whole view, or almost the whole view, of the electrical power systems. I will introduce the rest of the demos very quickly, and we will be able to see how we cover from the next generation control rooms for TSO, that is starting from the transmission level of the grid to all the way down to the very low voltage level and IoT, electrical communities, and so on. Yeah, That's the overall picture, and we will see the demos and where are located and their main goals in a minute. As for the goals, I will show them everyone. I will show every one of them all together, but we can focus on the first ones, which are the most specific of our technical innovations. eFORT is focused on cybersecurity and resilience of the power system. So it is within our expectations to contribute to a deep understanding of the vulnerabilities and risks. We have some interesting project-wise results and insights in that sense that we will mention in next. And once we have helped or we have contributed to have a more clear view of that, for sure we have to contribute to the technological side of making a more resilient, autonomous, and proactive power systems in terms of cybersecurity and resilience. For that, we will have developed a group of technologies that represent secure by design developments that help have, as I was saying, a robust power system defense technology. We do not forget about data sharing and the frameworks to collect, share, and manage data. We will see that we have been working also on a central platform, and as you can see there, secure grid framework addressing privacy and data management is also a key goal for us. And finally, all these developments, all these innovations combined together lead us to a set of operational technologies and strategies that prove in a practical way new mechanisms and strategies for resilience. These are validated in 4 demo sites. One of them is the Italian one, and I will move next to have a quick insight to this kind of developments and the demo sites. This is a very, very technology-oriented project. So as I was saying, we have solutions and technologies that are being carried out, and they are grouped more or less like this. I will mention the most significant advancements later, but just for you to know that we have several important building blocks, and we could highlight the intelligent platform as a central hub for tool execution and data sharing. A lot of technologies for asset management. The demo sites are really grid-oriented and demonstrating new strategies in transmission, distributions, and low voltage levels. For that, we have algorithms for cascading effects prevention, self-healing at different grid levels, IoT-related cybersecurity insights, islanding operations, edge devices, the secure box for parallel secure operation of the infrastructures, and the control room. And digital technologies that include augmented reality, blockchain, intrusion detection systems, and so on that are combined in the demo sites. So with no further ado, let's have a very quick look to the demo sites. We have 4 of them. The Italian one we will get into detail in the following panel sessions. But apart from that, we have the Spanish one, centered in a distribution substation all the way down to medium and voltage levels. In Delft, the Netherlands, we have operation of the transmission level with the control room of the future. And in Ukraine, Ilsi, we have a full-scale, a real operating substation that let us focus on the cybersecurity and secure design of substations and substation automation systems. This diagram here just shows that we have carried out an effort that we are quite proud of, that of linking together all the developments that are quite numerous with the demo sites, combining the technology to end users, the utilities, end user expectations and requirements to get a fruitful demonstration and validate each development in the demo sites, which is more convenient or more productive for each one and adapted, as I was saying, to operators' interests and benefits. So just a quick look to main developments and results of the eFORT project, and just a couple of mentions project-wise. We have a vulnerabilities database where we have carried out a comprehensive analysis and unifications of different sources and a combinations of vulnerabilities, threats, and a risk-based score arranged by grid domain, which represents, I would say, comprehensive, relevant, and significant information resource from the project that comes to life in a visualization dashboard with integrated hypothesis and risk evaluation. In the practical IoT side, which is at the lower voltage levels and have impact in all the power systems, we have shown from simulation and practical experiments that IoT attacks, IoT-centered attacks, can have an impact on the whole grid. We have dimensioned that. We have published some insights in that sense, and we have shown how the availability of distributed photovoltaic solar generations help mitigate that. We do have a central intelligent platform, and along these 4 years of the project, we have had the opportunity to see how the paradigm has changed from central aggregation data platforms to data sharing, more in like a data space point of view. It's not a data space, but the philosophy is data sharing rather than data aggregation. And also, as the left diagram shows, a dynamic support for interoperable, real-time and combined tool execution. As for the demos, just a very quick look. As we were saying, in Spain, we are focusing from the distribution substation to the low voltage level. We have conducted, or we are conducting there, blockchain-based registration, traceability of distributed energy resources. We have real-time parallel OT cybersecurity with edge devices installed on the substation, and we have had some more practical and related to the grid experiments of the IoT manipulation I was mentioning before. In the Netherlands, we have a full-scale control room setup of the future for training and demonstration. We have conducted ambitious algorithms there, such as cascading failure and restoration, based on real-world incidents, deep learning, and graph analysis combining cyber-physical attacks and effects. This will let us implement a scale system, as I was saying, and we plan on conducting practical red team, blue team, and training sessions there. As for Ukraine, we have a full-scale substations, and as I was saying, the main goal was secure design and secure operation. As for the design, we conducted some on-site scanning, leading to 3D modeling and BIM design of the substations, which digital information is being used for, again, secure access, traceability, and training of operators. We also have deployed there a laboratory demonstration to go on the cybersecurity investigations with edge-level intrusion detection systems that use existing datasets concocted from current IEC 6150 communications, showing how existing digital substation let us develop new tools or new cybersecurity approaches. And last but not least, or last and more important today, we have the Italian demo sites that will be introduced next. It is located distribution level again, quite a general view of several grid segments and generation assets. And we will see right away in our panel some concepts such as the develop a smart grid controller, some reinforcement learning approaches to manage islanding recuperation and overall resilience of the distribution level, and AI-enabled analytics applications and interesting concepts, very trendy today, such as these AI applications or human-in-the-loop concept that we will see in a minute. So that's all by my side from now. For me today, we will resume later. And now it's time for Giacomo Della Croce to go on with the introduction of the Italian demo site from a general perspective. Giacomo Della Croce is the electrical engineering manager in digital platforms. And Giacomo, the floor is yours. Thank you, everyone, and let us go with this type of the Italian demo site. Thank you.
Yes, thank you, Jesus, for the introduction. Okay, so good morning, everyone. Thank you for joining us today for the Italian pilot site workshop. It's really a pleasure and an honor for me to lead and represent the Italian working group. Today, I will briefly introduce the Italian demo and show how intelligent digital solutions and advanced control strategies are being developed and demonstrated in the pilot. So the Italian demo site, I want to start with the Italian demo site that is located in the Sarentino Valley, in the center of Südtirol. So we are in the north of Italy and precisely in the province of Bolzano. In this region, Edina operates as the main distribution system operator. And this region, due to characteristics of its territory, it's really full of hydroelectric power plants connected to the medium voltage grid. This creates both opportunities and operational challenges. One of the peculiarities of this grid is the presence of a lot of the so-called subtended DSOs that are capable, in any case, to operate in an independent way, as well as islanding mode, through automatic primary and secondary regulation of frequency and voltage by local controllers. So I can recap the technical innovation that the task of the project defined as main goals. At the core of the project, we implemented a digital twin of the power system with advanced data collection systems, state estimation, and load flow analysis. Then we investigate the control scheme for island mode operation, and with the grid analysis of this operation mode. Using, of course, the master and slave coordination strategies for this purpose. Then we integrate each feature in the intelligent dispatching platform, using also AI-based services. Finally, we provide also an innovative grid chatbot for customer and operator support tools. So these innovations allow us to simulate, monitor, and optimize grid behavior under different scenarios. And every feature have been included and integrated into Smart Grid Controller. You can see also the logos of our partners. So together with digital platforms, collaborate Edina, the DSO, Links Foundation, and Fraunhofer from Germany. So in this slide, you can see on the right the task that we presented at the beginning of the project, and the points that we we implemented. So digital twin, control scheme for islanding mode operation, then power services, for instance, power regulation, water monitoring, and peak saving, and finally, grid chatbot. But so how it works, so how smart grid controller works. One of the key features is the automatic grid restoration. So the system automatically reconstructs the grid topology of the grid based on DMS and SCADA configuration. In fact, it can subdivide the grid into feeders and uses static data based on nominal values stored in the database. Then we have the real-time operation. So it's another fundamental component of the smart grid controller that allow to do load flow calculation in real time. So the system updates this calculation every 4 to 7 seconds, depending on the configuration, and it calculates with mathematical methods some parameters like line currents, node voltages, voltage violations, and eventual network overloads. Smart grid controller also provides voltage profile analysis and interactive grid object panels for operator. This real-time visibility significantly enhances operational awareness and decision making. We also developed an AI-based chatbot for quick grid analysis and operator support. The platform uses separated real-time and historical databases combined with a back-end front-end architecture and a user-friendly human-machine interface. This allows operators to easily access information, run simulations, and analyze historical trends. You can see on the right the architecture of the solution, and let me point out the real-time protocol for the interface between the TSO platform and the smart grid controller, that is OPC1, very useful for the real-time communication. A central innovation of this project is the optimization of island operation. So the system supports basically the master-slave configuration and architecture and enables simulation of specific topology setups, pre-configured setups. It allows simulation of power set points for generators and provides a dedicated island view in the HMI. This makes it possible to evaluate and optimize islanding configurations before the real implementation. For the project, several case studies were conducted to validate the SGC platform. First, the monitoring and control scenarios were tested. Second, simulation platform scenarios included switch status evolution and seasonal daytime profiles, both winter and summer. Then we tested optimal islanding operation, including intentional islanding, optimal grid setup, and the so-called zero exchange algorithm. And finally, very good dynamic analysis were conducted. For the first case study, the generator coordination in island operation were evaluated under high and low power levels, comparing traditional methods with AI-based approaches. These case studies demonstrated the flexibility and the robustness of the solution for all the partners. So a brief presentation of impact and benefits of the solutions. The project that delivered important results. One major challenge was the accurate reconstruction of the electrical network topology and their parameters. The issues was that limited and or inconsistent data required extensive validation and assumption. This highlighted the importance of robust data collection strategies and flexible modeling approaches. Another key benefits is the optimized management of the grid portions operating island mode that requires real-time communications and advanced control strategies to maintain stability, reliability, and safety. Thanks to the implemented solution, coordination among the stakeholders and connected power elements has been significantly improved. So for conclusion, the Italian eFORT pilot demonstrated how digitalization and AI and advanced control strategies can enhance grid resilience, support renewable integration, and enable reliable island operation. The experience in Sorrentino Valley provides valuable insights that can be replicated in other European distribution networks. So thank you very much for your attention. I pass the ball again to Jesus and the panelists of the workshop of today. Thank you.
Giacomo, here we have the introduction of the overall developments, and with the upcoming presentations we will see in a more detail some of them. Next is Lorenzo Chiapponi, product marketing at Digital Platforms, and he will show us the first look to one of the developments, and this panel session will be centered on digitalization of power system through intelligent platforms with a more detailed view, as I was saying, of the smart grid controller. So Lorenzo, please, you can go on. Thank you.
Okay, thank you, Jesus. And welcome and good morning to all. And today I'm focused on digitalization of power system through intelligent platforms, specifically for the SCADA-SGC approach within this eFORT project. The key message is that the SCADA remains essential for monitoring and control, while SGC has an intelligence layer that helps operators to anticipate, validate, and execute decisions. And this is one of the fastest, most measurable impact is on the scheduled maintenance. And we have take a long reason about this point, and we can guarantee a safer outage planning, fewer rescues, lower customer impact, and today I will show you why this is urgent now, and why this approach is good, and why this SGC project have been a good experience for us. So why digitalize the grid operation now? We have three converging pressures now. One is about the renewables, variability and changes for operation conditions that are very frequent. The second is that we have tightened margins on voltage and thermal constraints on the networks that are closer to the limits. The third one is that we have aging assets that increase the volume and the complexity of planned interventions. In this way, we have some problems, and we try to give a solution for these problems. The solution is an intelligence layer, to put an intelligence layer inside your system. And with this intelligence layer, you can avoid manual checks, and you can lead to avoid last-minute surprises and reschedule. So in this way, digitalization can turn planned works into a network-aware, predictable process. The market trends, you know, is for platform-based operation. And we are moving toward platform-based operation through interoperable integration, reusable data models, modular apps, and generally speaking, AI-ready analytics. And some utilities want to add capabilities without replacing core system. In this way, the smart grid controller is aligned with this trend. It's only an intelligence layer on top on an existing SCADA that supports both daily operations and structured pilots with measurable outcomes. What exactly does the SGC beyond the SCADA? In this chart, you can view that there is a very simple framing. The SCADA tells you what is happening. The smart grid controller tells you what it means for the network and what could happen if you act. The SGC adds a richer operational picture derived from SCADA data and from the network model, gives a continuous assessment of constraint and margins, and a decision support via analytics and scenario capabilities. Last one is a platform approach that expands function over time. In this case, we have a complete chain, and the chain is composed by the existing SCADA, the smart grid controller, and on the field by the RTUs. And all of these points are connected by standard protocols typical from telecontrol and normally used by every DSO. For scheduled maintenance, this means that you can validate outage windows and the switching plane before execution, reducing operational risk and disruption. The capabilities are different and are about operational awareness for giving data from the network maps, the assets and alarms, and you can reconstruct the topology and feeder segmentation. On the analytics side, you can look for real-time load flow with configure refresh, and you can detect the limit of violation. You can give more support for decision with what-if simulation and operator advices. And this solution is integration ready. OPC UA is the standard protocol for that exchange with the SCADA, and we can give REST API and separate data stores for every other integration. About the architecture, the SGC sits on top of the operational infrastructure and integrates via standard protocols like SCADA to like OPC UA to the SCADA. It uses static network data from utilities repositories and can be deployed on-prem in the OT perimeter. The governance is clear. The SCADA stays in the system for record and control data. SGC generates derived intelligence, state and recommendation, and return to the operator via HMI and API. This approach enables an incremental low-risk adoption path. We can start with only with an advisor level. We can probe the values and then expand the solution. We can interact this process in a standard way. We can plan our activities before our action. We can operate and view the results during the action, and we can learn after our action. And all of this action can be iterated and can be controlled by the SGC together with the SCADA system. The benefits for the customer and the customer roles are different. For the TSO and for the DSO, we can give a scheduled maintenance that becomes repeatable with a digital workflow. We can choose the best window. We can reduce reschedules. We can minimize customer affected, and we can increase safety margins during planning outages. For researchers, we can give a real operational constraint and workflow to test methods, including maintenance-driven reconfiguration. For the project partner, we can give a common platform layer to integrate contributions and to demonstrate experimental results faster. For policymakers, we can give evidence-based improvement with less disruption from planned works, improved resilience, and a better use of existing infrastructure to support the renewables integration. For marketing professionals, this is a clear story that can help to predict maintenance, fewer disruptions, and generally speaking, a better quality of service for every role inside the value chain. For the innovation expert, the SGC is an AI-ready foundation, but is valuable for deterministic analytics and for making a scaling credible for the future. Last slide for me is about the conclusion. This project offer an SGC as an incremental step that leverages existing SCADA investment and can be turn over every SCADA. The differentiator for this project is that is a lean deployment method model and is a simple way to give an innovation. Is a scenario-driven operation with real-time analytics that are very important because give to operator a more deterministic way in their action, in their daily actions. On the strategic view, we are very open to modular architecture, and we have a digital twin mindset because we have designed the architecture in a complete digital way. And we are running on the path of AI to enable decision in an easy way to support the governance. Thank you for your time.
Thank you, Lorenzo. Very interesting presentation, and you clearly showed some in my opinion, very relevant aspects, such as, for example, how the current state of digital substation and digital data enables this kind of parallel added value operations, which can tools, this added value and new parallel tools, which can be executed in their own domain, as you were explaining, as a support for the operators and making the most of existing digitalization, which is one of the main goals of this kind of technologies, because if they do not provide some added value, new approaches to the grid, we will have just another generation of standard protection and control. Thank you. So
Thank you.
next is turn for Christian Destro, researcher at Links, who will guide us through some advanced algorithms, introducing also machine learning for advanced control of the grid, especially island in operation mode. So please, Christian, the room is yours.
Thank you, yes. Good morning, everyone. I'm Christian Destro, researcher at Links Foundation. And today I will present the use of machine learning techniques for islanding operation mode. First of all, what is islanding mode? Let's as image a normal power system supplied from high voltage or medium voltage to low voltage levels. Suddenly a fault occurs or a disconnection maneuvers is performed for maintenance. Two things can happen. Blackout, meaning loss of supply. Islanding operation, a condition in which a portion of electric network continues operation autonomously after being is disconnected from the main grid. Why this happened? For many decades, the power system was designed according to a strongly centralized paradigm. Generation was concentrated in large thermal and hydroelectric power plants, while loads were geographically distributed and supplied through hierarchical transmission and distribution networks. With the energy transition, the system began integrated and increasing the number of renewable sources, such as PV and wind plant. This new generation units have characteristics that are fundamentally different from traditional power plant. The power system therefore started losing its purely centralized structure, becoming more complex and less predictable. The most significant evolution has been the widespread deployment of distributed generation, particularly rooftop photovoltaic system and residential and industrial buildings. This gave rise to the concept of the prosumer, and entity that simultaneously consumes and produces energy. The distribution grid is not longer a passive system, but an active one, where thousands of small generation influences the overall network behavior. The transition toward highly distributed generation has not only modified the physical structure of the grid, but also fundamentally changed its dynamic and operational behavior. In traditional centralized system, frequency stability was guaranteed by the high inertial of a large synchronous machine. Voltage was concentrated in a few strategic nodes. Protection systems were designed for an unidirectional power flow. With massive integration of distributed energy researchers, DER, the grid becomes less inertial, more variable, characterized by bidirectional power flows, more exposed to operating conditions not foreseen in the original design. In the centralized paradigm, islanding was a rare and undesired event. In modern system with high renewable penetration, it becomes a resilience strategy and a mechanism to guarantee continuity of service. An emergency management tool. However, operating is in islanded mode require local balance between generation and load, autonomous control of frequency and voltage, coordination between inverter and storage system, adaptive protective strategy. And when generation is highly distribution among prosumer and small plants, centralized management becomes less effective. That is where distributed control system, predictive algorithms, a based solution, multi-agent coordination strategy become relevant. And the objective is not only to prevent system collapse, but to make the grid adaptive, capable of dynamic configuration, isolation when necessary, and local stability in maintenance. To achieve this is essential to know the network topology and configuration. Understanding how the network will behave is equally important. Therefore, being able to forecast is essential. Short-term load forecasting, STLF, covering horizons from a few minutes to a few hours, represents a critical function in power systems. Accurate STLF allows a real-time optimize of supply-demand balance, improving efficiency, reducing cost, and increasing reliability. At the distribution level, precise short-term load forecasts support control system and resource scheduling and stability maintenance. This is particularly important in islanded operation, where operation must really rely on local generation and storage. Forecasting enables anticipation of load variations and adjustment of generation to maintain a stable frequency and voltage. Below, we can observe several traditional methods of emerging ML-based approach, ML machine learning. In general, AI model outperform statistically when sufficient data are available, thanks to their ability to capture complex and nonlinear patterns. Commercial and open source tools for STLF are already adopted by distribution companies. OpenSTLF is collaborative open source project providing automated machine learning pipeline for short-term energy forecasting. SAS energy forecasting offers cloud-based short-term forecasting service using techniques such as GLM, RIMA, and neural networks to produce a robust prediction. These tools are used in control rooms to support rapid decisions, achieve mean absolute percentage error, MAPA, around 2%. Yeah. The next step is to use network data and forecast results to determine which control action minimize instability, cost, and risk of collapse. This leads us to advanced control system currently used after forecasting. The most widely adopted model is islanded microgrids. In the three-level hierarchical control structure, we have primary control, timescale millisecond, a few seconds. Objective, the objective, immediate stability of frequency and voltage, methodology drop, power, frequency, and reactive frequency and voltage, where frequency is regulated through active power and voltage through reactive power. Secondary control, is the inverse. Time scale is second and minutes. Objective, restore exactly nominal frequency and nominal voltage. The last one is tertiary control, timescale minutes, hours, objective, economic, and operational optimization. Our focus is secondary control, since due to its time scale and dynamic nature, several machine learning systems are sustainable for this level, specifically reinforcement learning. Reinforcement learning is a branch of machine learning in which an agent learns to make decisions by interacting with an environment formalized as a Markov decision process, MDP. At each discrete step, the agent observes the current state, takes action that perturbs the environment, and receives a reward indicating the quality of resulting state. Through repeating exploration and exploitation, the agent learns a policy that maximizes cumulative reward. In deeper reinforcement learning, neural network approximate value function or policies, enabling handling of high-dimensional inputs and complex nonlinear systems. The transitions toward reinforcement learning isn't a replacement of traditional controls, but a current evolution driven by increasing grid complexity, high DER penetration, the need for local resilience. Let us now consider a case study. Case study, deep reinforcement learning for secondary control in islanded microgrids. Concerning the discussion, we consider a real application of reinforcement learning to islanded operation presented in recent research. The paper addresses well-known issues. Microgrids are low inertial system. They exhibit high renewable penetration. They experience frequent topological and operational variations. Classical controllers and are strongly model dependent. The authors show that traditional secondary controls, drop-based or PI-based, are not sufficiently adaptive to nonlinear microgrid dynamics. The hierarchical system is therefore modified at the secondary level. The algorithm used the DDPG, deep deterministic policy gradient. The agent state include the synchronous generator frequency, PCC voltage, local base voltage, error with respect to nominal values, current and previous system states. The agent control active and reactive power of the two base. The action space in continuous making DDPG appropriate. Reward function, the reward penalizes frequency deviation, voltage deviation, PCC, and local nodes. Extreme operation conditions. It's designed to minimize dynamic errors and maintain stability under disturbances. They test three scenarios. Three critical events were simulated: feeder disconnection, three-phase fault event, abrupt load shedding. The agent was trained only on the first scenario, but tested on all three. The result on table that we can see. Overall, a reduction is cumulative error was observed, expect drop, normally secondary control. In same cases, voltage error was reduced almost to zero. Dynamic deviation were lower compared to drop. Most importantly, the DDPG improved the stability even a scenario not seen during training. This demonstrated that reinforcement learning can operate also as a really secondary control. It can outperform drop-based logic. It doesn't require an explicit analytical system model. It's robust to topical variations. In other words, control becomes adaptive and data-driven rather than purely reactive. Islanding is not longer an event to be managed with rigid statistic controls. It's a dynamic, uncertain, multivariable problem. Literature evidence show that reinforcement learning is not only theoretical, but already tested in realistic islanded microgrid scenarios. The next step is to integrate forecasting, hierarchical control, and adaptive learning into a unified operational framework to make grid truly resilient. Thank you very much.
Thank you, Christian. I think it was very interesting for everyone to recap the concept of the impact of distributed approach of the grid, which I would say it was bring us all and all these kind of projects here, this change of grid natures that put us through several relevant challenges, and a good opportunity to see, I think, the importance of forecasting, short-term forecasting, and how advanced techniques with machine learning and deep learning contribute to that. So thank you, and let's move on to the next panel, the third one of today. Before doing that, let me remind the audience that they have the option to share their questions. Our moderators have enabled the Q&A window for that, and some questions come up. We will add them to the ones I will present to the speakers. So, with no further ado, third and last panel of today by Patrick Jacon, who is grid analyst at EDINA, and will share with us a first-hand impression from the grid operator of this demo site. Thank you.
Okay. Hello, everybody. I am Patrick Jacon. I have 6 years of experience at EDINA, and I currently work in the grid analysis department. And first of all, I would like to introduce my company, our grid, and the scenario where we operate. EDINA is a DSO operating in the Italian region of Südtirol in the north of Italy. Founded in 2016, EDINA has been a business unit of the APERA Group. That's an Italian energy group based in Bolzano, and focused on renewable energy production, distribution, and sale of sustainable energy services. Today, EDINA manages an electricity distribution network of approximately 9,400 kilometers, covering low, medium, and high voltage lines, as well as all related plants like HV, MV, and MV-LV transformation stations. And in addition, we are responsible for the natural gas distribution service in the city of Merano, next to Bolzano. Our grid structure reflects the size and the complexity of the territory we serve. It includes more than 5,200 kilometers of low voltage lines, almost 4,000 kilometers of medium voltage lines, and around 146 kilometers of high voltage lines. Approximately 80% of our grid is composed of underground cables, which improves the reliability and the visual impact, but also introduces some specific challenges in terms of fault location, maintenance, and operational flexibility, especially in the mountainous areas. As shown in this graphical representation, the network covers almost the entire region, which is largely mountainous and therefore particularly challenging from an operational point of view, In the municipalities where we are not present, there are present the so-called sub-distributors, which are interconnected with our medium voltage grid. A significant amount of renewable energy generation capacity is connected to our grid. This includes more than 300 megawatts of solar power, over 320 megawatts of hydropower, and as well as storage systems and other generation sources like biomass power plants or cogeneration plants. Depending on their installed capacity, producers are connected either to the low voltage or to the medium voltage network. And as you can see here, producers are spread homogeneously across the whole network. And this high penetration of distributed energy resources is I think the key feature of our grid, of our system, and but it also introduces some operational challenges. One of the main issues we face is related to the voltage regulation. In some areas, because of the graphical layout, medium voltage lines can be very long. And when generators are connected along these lines, especially during emergency conditions, they may cause significant voltage problems. And for example, in this figure, and the red areas represent over voltage conditions, and the blue areas represent under voltage conditions. And then, another important challenge is the network variability. The behavior of the grid can change significantly from season to season. For example, during the summer months, electricity production by PV systems is often very high, and which can lead to over voltage situations. And on the other hand, in winter, higher loads combined with lower generation may result in the opposite effect. Operator safety is also a critical aspect. Network operators must always place earthing points very carefully to avoid keeping a line energized by generator that is still feeding the network. And these risks exist on the medium and also on the low voltage network, and it requires strict operational procedures. In addition, user protection settings play a fundamental role. Users must configure correctly the protection system on their plans to ensure selectivity with our grid. And this is essential to prevent that a fault on the user grid can cause outages on the distribution grid, also on the DINA grid. And okay. And finally, the management of primary substations is becoming complex in some areas, because at some periods of the year, when the local production is very high, some primary substations may operate in injection mode towards the high voltage grid. At other times of the year, when the loads increase, they switch to withdrawal mode. And here in this slide, you can see two examples of two primary substations of EDINA. As showing the graph, the positive values correspond to the injection mode into the high voltage grid, while negative values correspond to absorption grid. And yeah, I think that managing this dynamic behavior is the key challenge of for modern distribution operators, and the goal should be to address and improve all these critical aspects that we saw in these slides in order to make the electrical system more resilient and stable and sustainable. And that's all from my side. Thank you for the attention.
Thank you, Patrick. As we were saying, we are really glad to have the direct view of the distribution system operator, and you provide us a real practical image of the problems that the new disposition and architecture of the grids are presenting, and these kind of projects solve. So thank you all. We at CIRCE, as part of the coordinator team as coordinators of eFORT project, we are glad to have such powerful and advanced demo sites. And yes, thank you all for your presentation, and I hope that the audience got representative image of what we are achieving within the project. And your slides just prove what I was saying about the technology-oriented nature of this project, as well as the technology validation we are carrying out at real scale and relevant segments of the grid. So thank you all. Time now, we are 10 minutes behind of schedule, nothing serious. We have now our Q&A session, our open debate sessions, and we have enough margin to have a calm, productive, hopefully, debate. So we will pay attention to the meeting resources to see if we collect some questions. But in any case, we are ready to go on with the debate, and let me, if you will, deploy a first round of questions following the order of the presentation. So I will start with Lorenzo, which introduce us to the smart grid controller. So I remarked here the importance of how meaningful it is to introduce the human controls, the AI, parallel operation, advanced operation for the operators to achieve more capabilities and to be able to conduct new use cases and a more deep, better operation of the grid. And in terms of that AI human collaboration, a trending topic today, we would like to know your view on what level of supervision by the operator is required, even in the presence of AI-based recommendations. How important is that, and what do we need from the operator in these new scenarios?
Okay, thank you, Jesus. The operator is very involved in this scenario, and is the main actor in this project, because we focus that lied to the operators are several may create several problems and several issues, and with this solution, with the SGC, for example, an operator can change these habits and can create value in a different way. And he can schedule activities, he can start to plan and verify step by step every changes. And in this way, he can avoid problems. He can use AI, and he can use the workflow set inside the system to avoid problems, because these tools can help every operator to prevent issues and to enhance service levels for the customers, especially in a scenario like EDINA scenario, with a lot of distributed generators, different territory, difficult in the grid, and for islanding modes. And is a different approach to the operator.
Okay, thank you, Lorenzo. Yeah, there is no doubt in, and I would say that assisted operation is as we are saying a trending topic for the next generation operation of the grid and the introduction of AI. So it's a very good thing. I think that we have the chance to have a first look at this within the project. So, well, next, let me continue with this first round. So next is Christian. And given that you also presented us a machine learning, deep learning based approach, I think that the same question or similar one is in place. What do you think of the supervision in your case of this reinforcement learning algorithm that is maybe more autonomous than SCADA-based recommendation? What do you think of the human level supervision and the traceability of the decisions made by the reinforcement learning and this kind of AI-based controllers?
Even when AI-based control is managing frequency and voltage, a significant level of supervision by the control room operator is still required. AI should not operate as a fully autonomous black box, especially in critical infrastructures such as power systems. The operator must retain a supervisory authority, real-time visibility of system states, and the ability to override or detect the AI if necessary. In practice, AI-based control should initially operate in advisory or shadow mode, then move to supervised closed loop operation, where classical control remains available as a fallback. The goal is not to remove the operator from the loop, but to shift the role from direct control to high-level supervision, anomaly detection, and decision validation. Ultimately, responsibility for system security must remain with the human operator, supported but not replaced by AI, I think. So.
Yeah, fully agree with your view, and this kind of governance roles, responsibilities are key critical issues when introducing this kind of algorithms. And it's interesting because both Lorenzo and yourself introduced, in my opinion, two different planes of this AI-assisted operation. As I was saying, more the SCADA-like operation, more human time-wise operation and control of the assets, and some more deep algorithms that take decisions which are more related with the grid topology, grid magnitudes, and so on. So the traceability and supervision needs remain for both cases. The goal is similar, but the implications may differ. So it's good we take a look at these two kind of examples. So to finish the first round, Patrick, one of the most interesting things for both the second and third panels, I already said that, is understanding the implications of these changes in the grid when we have to manage distributed resources and dispersed generation. So I would like to ask you, how are generation plants managed in your case from the distribution system operator? Can you operate on them remotely to disconnect them or control their contribution to the grid? Which type of plants are able to this kind of controls? How? What can you tell us about that?
Okay, yeah. Generator plants are managed by the coordination between the TSO, also the transmission system operator, and the distribution system operator. And in Italy, we have the so-called RIGEDI framework. And for some medium voltage generation plants, remote disconnection is possible. And in particular, for plants with a power greater than 100 kilowatts. And these plants are, for these plants, we need to call them, and we need to be able to remove them remotely from the grid. And also under the RIGEDI, the DSO ensures that these plants are equipped with a remote disconnection system, and we can disconnect them from the grid when the DSO requested this to us, and directly from the control room of EDINA, of the DSO. And at the moment, I said also that we need to we are able to disconnect the plants connected on the medium voltage grid, and with a power that's greater to than 100 kilowatts. But I think looking ahead, we will need in the future year similar control and management capabilities for smaller generation plants connected to the low voltage network, and not only for big plants connected on the medium to the medium voltage grid.
Okay, good. Yes, this is an interesting topic, I think, because even from the perspective of dissemination, because experts and people which are not really close to grid operation may not be aware of how necessary and even frequent are these kind of operation on disconnection. Even at a Europe level, the approaches to demand side control requested by the TSO or by the market differs. We have several approaches to that. It's an everyday issue. For example, in the grid in Spain, curtailment is a reality. It directly affects to disconnection of generation plants, not directly, or not as in your case, as part of the distribution system operations activities, but more by a market necessity or a system necessity. But anyway, that's a technology that sometimes may seem that belongs to the realm of this kind of big research project, but I would like to highlight that it's a daily reality today. So thank you everyone for your responses. I'm seeing that we have questions from the audience in the panel. So thank you everyone for this, and I think that it's only natural that we give place to them. So given that we are with you, Patrick, I think that one of the first one we have may be addressed by you, but from now on, there are open questions. Feel free to address them as you may like from these ones from the audience. But we have one, as I said, Daniel is asking what are the main causes of what causes the power fluctuations in the power stations of the demo sites. What do you think? What will you remark as main causes?
Okay, yes, of course. I think that the installation of the CCE is very important, also for the DSO, because we can see in real time the characteristic of the plants and also the voltage, and that's not possible with plants where the CCE is not installed. Also, I think it's very important to have the CCE on the grid, and the only problem is that at the moment we have some problems with the installation, also to explain on the clients what they have to do for the installation of this instrument.
Do you mean these know-how issues are they related, just for me to understand, are they related to the deployment and installation by the contracting staff or by the end users who need to operate this kind of tools?
No, because for the deadlines that we have, it's important that all the clients which have big plans install this controller.
Yeah. Okay, I see. Yeah, that's something. Even if we are remarking the benefits of digital systems in terms of enabling this kind of new tools in a very quick way or a practical way. If not quick, projects like eFORT prove that new tools, new AI-based operation is possible, and you can, as of today, install it and use it. But there is, as Patrick is saying, there is this know-how gap, mainly because of pressure and deadlines for the day-to-day operation, or for, just as we are saying, different interests and priorities between the current or daily operation and new training, deployment, and integration of new procedures. So a very interesting view indeed. So given that you are attracting a lot of attention, Patrick, let's move now to an open-ended questions that I had also in mind, and I think it is a very natural question in this kind of projects. And Brenda from the audience is asking us, what are the main lessons learned so far that could be useful, both from, I would say, she's saying for similar projects, for further research, of course, but I would say also for us as insights or tips for deployment of the solution. What would you say, any one of you, main lessons learned in terms of or from these solutions and demo site?
From my point of view, a first lesson to learn is not necessary to have a huge project to go to the field. You can start with the smallest project. For example, we have had an approach for the digital twin that is a not complete digital twin, but it was a pragmatical approach. And we only focus on topology, on the state estimation and the scenario, and only one scenario, not all scenarios available on the market, but is a useful approach to start innovation and to start control the grid. This is, for me, a big lesson.
Yeah, I fully agree. That's we have to push this practical view because technology is there. We need to use it, and maybe for empowering that use, as you said, specific or scopes or grid segments make it easier to learn how to use it, integrate these solutions, and starting getting their benefits. So yeah, I think that's a good lesson. Christian, anything from your side? Lessons learned from this deep work of eFORT?
I was thinking, honestly, I think the importance in that project and also in another project that I follow, the importance of the data that we can collect from the project, because we know more or less all the stuff about electrical system or something like that, but now we trying to learning at the new brain that we are creating with algorithms, with the neural network, with the reinforcement learning, and we need the data are really important to have a more complete algorithm project possible. That's what I learned in this specifically project, but also in another project that I follow that are similar.
Yeah, I fully agree. Data is the basis for every application. I think power grids are well positioned there. because of the current level of digitalization, strong market standards like IEC 61850 that we are using in these demo sites, or smart metering are good examples of that. And yes, every reference, every source agrees on the importance of data interoperability and data quality and sharing and governance. We should not forget that. Data has to be shared, has to be used, has to be stored, but in a safe, control, and privacy assurance way, which are aspects that also are taken care of in eFORT. And Giacomo, since you have the overall visions of the demo site, and I don't want you to be bored, let me ask you as well for lessons learned. Is there anything special you want to highlight from this demo site experience?
Yes, as I already to tell before, the importance of a real-time communication protocol to be used. So both from field side and of course from parallel tools at the TSO control room level. So we use the OPC-UA interface that enable safety and reliable communication from database. So a very technical aspect, but when you realize the practical demo, they are very important and can bring some issues and problems.
Yes, that's an interesting addition, Giacomo. Thank you. As technology center, I'm a technology developer and demonstrator, and I couldn't agree more, because sandboxes or initial developments, development environments can handle it all. But if we are moving new applications to operation mainly, you need, as you correctly address, you need that real-time data exchange. And that usually comes with practical needs, right? You need to install, to enable communication links. If they are not enabled, you have to do it in a safe way, and you need to collect that data in the all the dispersed sites or the central level where computing takes place and the algorithms are executed. So completely agree. And about security, we have a recent question from the audience that precisely address cybersecurity. And Patrick, we go back to you, because I think that your view from the DSO is, as we were saying, is a good opportunity to have a first-hand look to this kind of issues. And Giovanni is asking us about cybersecurity. He's interested in knowing if you have technology or platforms already in place for monitoring cybersecurity incidents and handle the associated responses.
Okay, yes, of course, but I don't work for this path in my company. Also, I don't know. I can give a technical good response on this question.
From your perspective, sorry, as grid analyst, are you perceiving within your company procedures or regulations, internal standardization and procedures, are you perceiving the importance of cybersecurity and the presence of these kind of tools and functions?
Yes, of course. So I think, yeah.
Would you say that it is, I guess that we discussed previously this know-how gap, because, everyone at the grid operation, we have to move from the pure electrical knowledge and electrical operation of the grid to this kind of technology literacy, where everybody need to know the importance of interoperability, data collection, communications, and cybersecurity. So Do you think do you feel as grid analyst that this kind of know-how gap is an important challenge for everyone in the sector to learn about this kind of cybersecurity needs? And what do you think we need for a better understanding of that, in your view?
Yes, I think that the cooperation with the different the different operators of the energy path is very important in these terms, and I think that project like eFORT could be important for this, to create a great communication with the oil companies, and yeah, I think in these terms also the cybersecurity is important.
Yes, a challenge. So, okay.
Yeah.
Let me get back to you, Lorenzo. And since we are talking now about this knowledge gap and all these trending topics in smart grids, let me share with you another key term or trending topic, which is the digital twin. Would you say that the smart grid controllers you presented can be considered as a digital twin?
Yes, can be. Can be, and as I said, is a little digital twin, but is useful to demonstrate that the model is good, and this approach is a good approach, and the idea is a good idea to innovate, and it's not useful to create a big model, but you have to create a model that can reply the main part of the reality, and this is enough to demonstrate the benefits on the grids for this approach, for the SGC, for islands scenarios, and so on. And only a small answer for the previous question. And as a producer and as a developer, we suggest to remain at the state of the art of cybersecurity that is available now on the market. Every vendor has a solution, and we cannot guarantee the security of the grid if we don't use the latest version of cybersecurity, latest version of certificates and TLS and protocols and so on. And inside this demo, we have do this, and we are proud for this, and we demonstrate that all the chain can be cyber secured on the embedded side, on the protocol side, and the application side, and this is very, very important.
Yeah, very, very interesting topic indeed, and more even if we think that we are showcasing a cybersecurity project. Would you like to further give us some details about the solutions that have been deployed in terms of cybersecurity in the demo site? Are they signature based? Do they use some kind of machine learning or intelligence? What can you tell us?
But we had cybersecurity activated on the protocols like IEC 62351, and TLS inside OPC UA, and role-based authentication for the users, for example. And this is enough for this demonstration. But in our idea and in our vision is one standard feature that we need to have in every installation now.
Yes, that's right. Basic. You describe the initial steps, cipher of the communication, secure authentication, and so on. Is there any other relevant function or path to explore that do you expect from your company perspective, that from your provider perspective, which are the next interesting steps regarding cybersecurity functions, something more for the future or advanced? What do we need to explore or test?
for the future, and is first we have to expand the knowledge about it, and this is the first step. And the second
something
one,
like Patrick also mentioned. Yeah, I agree.
yeah, it's very important inside the company, on the vendor side, and on the final customer side. Is important too for for example, a little producer for a renewable is important too, that have to embed the cybersecurity inside their little plant. Is not only for DSO the problem, but the problem can expand to the far territory.
For sure. The problem within resilience and cybersecurity incidents, that's a key characteristic. They are expansive. They have cascading effects, and they can affect every agent in the grid, right?
Yeah.
Okay, thank you. So we discussed the lessons learned to give room to the audience questions, but I think that another general aspect worth mentioning is the challenges, because we are mentioning a lot how this technology is ready, how it can be used right away, that this is a reality, and I don't want to underestimate the technology level of development and the challenges we have gone through the project. So I would like to go now to Christian, and since you have dealt with several technology advanced aspects such as reinforced learning in an operational environment, what would you say was the most challenging part of that development? Training, designing of goal functions, deployment. What can you tell us?
Yeah, I think training, for the reason that I said before. So to find the good data, to training the algorithm, because knowing the topology, having a good forecast, we can write a good algorithm. It's not easy, but we can. We know how to do it. So the testing is important part, and the challenge aspect about to improve the algorithm, because you need many data to do it. It's not easy, and the problem that every writer of code has. So I think is that additionally guaranteeing that the trained agent generalized to unseen distributions and different topology was a major challenge, also one of a major challenge. But yeah, I think the training to develop the algorithm, yes.
Yeah, it sounds reasonable, yes, because the informal learning, correct me if I'm wrong, the training presents a different nature from the usual training and validation data sets of more classic machine learning approaches. You have to be very careful with the reward signals you provide to the algorithms and how to teach it and guide it through the desired result. So I think that's really important. Any open question to the rest of the panelists, including Giacomo? Is there some other challenges you want to mention to build up on the conclusions and lessons from these demo sites? Any other relevant challenge?
For the project, we work for the future. Sorry.
Whatever you like. It can be a challenge coming from the project or an identified challenge for the future, as you like.
Yeah, the challenge of the project were to make a and provide to the DSO a platform, the intelligent platform that in parallel could add functionality to the existing SCADA. So without great problem to the existing SCADA, go running a intelligent platform that work in parallel and with all cybersecurity level that enable the DSO to be in a safety conditions. So this is a very important challenge for us, and that we were able to do. For the future, of course, our interest is to investigate the way to include more parameters of the grid, so refine our model as a digital twin, and create the condition to improve also the controlling direction operation.
Good, relevant challenges for the future, of course, and they are very well related and linked to the ones we are seeing from the project and we are discussing today. Okay, so it's time. We thank you all for your contributions to the debate. It's time now for the wrap up and conclusions. And I would like just to give you a few headlines from what we've discussed so far. I would say, well, we had the opportunity to take a deep look of one of our demo sites. The project is, as I said before, more or less 6 months to its end. So we had the chance to see several advanced development, such as the smart grid controller, reinforced learning for islanding operation and grid forecasting, and the needs and view of grid operation and generation control from the DSO. From that, I would like to highlight first the good news. We have seen validated, proven solutions. The digitalization enables new tools that can use existing data and can be executed in a parallel or additional way to the existing critical systems. That is only beneficial for the operators because these kind of tools and solutions introduce a new layer of assistance, and that led us to the importance of the human in the loop concept. We may have AI-based assistance. I think that the power system are a very suitable field for this, but we have to be really careful, and precisely we are dealing with resilience and security of the grid. So caution and precaution is mandatory, and when it comes to AI, we need to be very sure about the data we are using, the quality of the data we are using and representativeness, and the traceability of the decisions that are supporting the operators. As for the challenges, I think all the panelists and myself in the session agree on the importance of cybersecurity, which is a challenge on its own in terms of knowledge, know-how gap, new procedures, and deployment of solutions that are already there, as Lorenzo said, but as Giacomo just described, present relevant challenges or issues to be tackled. And everything of this came from the general view of the grid that maybe a sentence or some concepts that are starting to get a bit repetitive in the sector. You know, the change of nature of the grid from more sequential systems to distributed generations, renewable integration, and so on. But in spite of being a lot of being concepts that we hear a lot, I hope this seminar, this project, and this demo site help everybody to see that these are more than good sentences. This is a reality. Grid operators and grid sections are facing these problems. These problems represent the need for advanced operation, and eFORT has showcased how this operation can be real and combining in a very sensible way, I would say, problem solving with awareness of the challenges ahead. So from Circe and myself, thank you all the panelists. I'm really happy to see how where eFORT is leading to us, the position we have to face the final months of the projects and the results we are delivering. And let me just for our panelists a final round where you can you may if you like, you may summarize your impressions of this session in 1 or 2 sentences, just a quick headline of what you had from this session or a final message you want to share. Giacomo, I'll give you the room as the overall demo representative, and we will go on with the rest of the panelists. What's your headline, your summary of today's session, or your final message?
Yeah, I want simply to thanks to our partner in the working group for Italy, for Italian demo. So after almost 3 years of work, we arrive at good results, very interesting topic. So just our thanks to our partner.
Okay, thank you. Fully agree with that acknowledgement. Lorenzo, anything on your side?
No, thank you, Jesus, for your resume and your vision, and thank you to the other panelists. We hope to replicate this solution in another DSO, in another territory, in another country, because all the things that we have talked about are real, and we can have a big good news for this innovation all around Europe.
Thank you. Yes, an interesting point. I think that another advantage of digital-based solutions is precisely replicability and scalability. So yeah, very interesting. Christian, final words?
Yeah, I would like to echo the previous thanks at the colleagues here and the partners. And I would like to replicate the digital twin test also in a real electric network. So that is always the difficult stuff in the project, replicating real world. But I would like to try.
Yeah, the continuity and further uses of the solutions of these projects. But I think this demo site is a living proof that solutions are real and solutions are being applied thanks to the presence of DSO, EDINA, and their willingness to test the solutions. So, Patrick, any final statements on your side?
Yes, I'm happy to collaborate for this project, and I'm glad to all the partners and the colleagues who works with me. And for me and I think we are working all together for the future of the energy path, and I'm happy for this.
Okay, Patrick, so thank you all. And last but not least, thanks to my Circe colleagues and Carla in the background of the organization. And the room is yours also, Carla. Thank you for being there. And you may say your final words and considerations now.
So thank you very much, Jesus. Thank you all for your participation, and thanks to the speakers for their interesting presentations and discussions today. As a reminder, until the end of the project in August, we will be organizing the other 3 pilot workshops. So the next will focus on the Spanish pilot side, and it's scheduled for March. So we invite you to stay tuned if you want to participate to this workshop. You can follow all the project updates on our LinkedIn page and on the project website, where you can also find the contacts of the Italian pilot site leaders and of the project team in general, in case you have any other questions or remarks during the next weeks or months. We really appreciate your time and engagement. eFORT is being a very successful project, and we are proud of being part of it. And we look forward to seeing you at the next workshop. So thank you very much, and have a nice day.